Hello, apes. We're going to start part one of water use and pollution. You guys just took your quiz, and your homework or classwork is to do part one of the study guide questions. So I'm going to link these short little YouTube videos to your Ed puzzle that you guys are going to do when you have your lab block this week. So part one is water use and groundwater. We've already mentioned that agriculture uses the most water in the world. So agriculture uses 70%, and most of it is irrigation of arid and semi-arid land. Industry is 20%. Paper and pulp mills use the most water, and then residential and commercial use the last 10%. Inside the house, it's flushing your toilets, and outside the house, it's watering lawns that uses the most water. We waste a lot of water. 65 to 70% of the water that we actually use is lost through evaporation, leaks, and other losses. Most of that is through agriculture. Um, Water is underpriced through government subsidies, especially in the US. The water that comes out of your tap, you pay about 1 cent per gallon. About 60% of the world's irrigation water is wasted, but we can actually improve our irrigation techniques and cut that waste using things like drip irrigation and center pivot low pressure sprinklers. Water conservation isn't asking people not to use water, it's just to conserve the amount of water that you're using, just use less of it. So, in a lot of places in the country, they actually don't pay for the amount of water that they use. It's just you pay a flat fee, and whatever it is you use, you use. And in Boulder, Colorado, when they introduced water meters, water use per person dropped by 40% because people were now paying for it and they were realizing how much they were using. It's like if you pay for your own gas, you really are aware of how much you use. And when those gas prices go up, you feel it. There are a lot of different ways that you can reduce industrial water waste. And one of those big things is stricter laws, providing incentives to conserve water, giving tax breaks to those who conserve water, taxing those who use too much of it. And so the potential to actually conserve water is huge. Um, there's a lot of water that you don't think of, and we call that virtual water, and sometimes it's water footprints. So this is indirect water use. So we use a lot of water per day in the US. The average use is 80 gallons of water, about 260 liters. It's probably more if you're a teenager that takes like 30, 40-minute showers. So flushing toilets, washing clothes, taking showers, running faucets, you have a lot of water that you use. And the world's poorest use 3 gallons of water a day, if they're using that much. Okay. But the most water that we use is virtual water. It's that water that we can't actually see. So it's the water in raising a pig and raising a cow that we're actually then eating. Remember when we were talking about the energy used to grow a cow versus the energy used to like grow soybeans? You have a lot of water, a lot of land, a lot of food that goes into it that water is then used to grow. So 1 pound of pork, not a whole pig, just a pound of pork takes 576 gallons of water. Okay, it takes 1.9 pounds of grain and then 52.8 gallons of additional water for drinking and processing. Okay, and that's that 576. A pound of beef is almost 1,800 gallons of water for 1 pound of beef. That's it. Your tea versus your coffee. Okay, coffee on the top, 880 gallons of water to produce 1 gallon of coffee. And you're like, but for me to make coffee, that's not how it works. But it's all of that water that goes into growing those beans. And coffee is a very water intensive plant. Or versus a gallon of tea only takes 128 gallons to create. All right, going to rice versus corn. Rice is more water intensive. It grows in terraces and it grows in a lot of water. 449 gallons of water to grow 1 pound of rice and 108 gallons of water to grow 1 pound of corn. So then moving on to paper and cotton. 500 sheets of paper take 1,321 gallons of water. And that's water to create the paper and water to grow the trees to then pulp into paper. Your cotton t-shirt requires 713 gallons of water. Okay. 45% of that is for irrigation, 41% is rainwater that evaporates off of cotton fields, and 14% is for treating wastewater from the fields and the factories. You don't think about that. When we flush, it just goes away. We're going to learn about that at the end here. Right. So this is our fresh water. You have the majority of it that's frozen in the polar ice caps, in your poles, your glaciers and stuff. So this is 30% of the fresh water on Earth. The dog's doing laps is surface water. Okay, the amount that is not frozen in glaciers and lakes. So this is different areas where you have groundwater. I'm sorry, this is groundwater and aquifers. This is your surface water. So 0.3% of the water is in surface water. You remember this map? Oh, Ruby wants to make an appearance. Say hi. This is your surface water. Here, we're going to talk about this. This is the Colorado River watershed. And up here on the East Coast, you can see all of the small watersheds. So groundwater is water that's underneath the ground. And I think there's a big misconception of this. It's not like a lake that is randomly found underground. The water is actually stored in the spaces of the soil. So when we were doing sand versus clay, sand has those big pore spaces. The water is stored in those spaces. It's like taking gravel. If I had a cup of gravel and I poured water in and then I stuck a straw in, I could suck the water out from inside of this gravel, because as I drink the water, more water is because of gravity, it's going to go down. All right. So that's what groundwater is. It's the water that's stored in spaces between soil, gravel, and rock. Your water table is the upper level of groundwater. Okay. So when you're at the beach, you dig, 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 and you're like, I hit water. If you were inland and you hit water, that's your water table. And then groundwater recharge is when the rain falls, water falls, or it can even happen underneath a lake. And what happens is the water goes through the soil and then it hits an impervious layer and it kind of like hangs out there. So we have what are called confined and unconfined aquifers. So an unconfined aquifer, if you look at this layer here, it has dirt above it. And that water infiltrates down through the soil and it comes into this unconfined aquifer, which looks like a stream, and it's not really there. And then here you have a confined aquifer because on either side of it, it has less permeable material like clay or impervious rock. And it only has one recharge area over here where the water can actually get into it. So that has its good and its bad. So an unconfined aquifer is just porous rock covered by soil. Water can flow in easily and out of that unconfined aquifer. Whereas a confined aquifer is surrounded almost all the way by impenetrable rock, and it has a smaller recharge area. So your confined aquifers, okay, not much is getting to them. They recharge very slowly, like 10,000, 20,000 years, very, very slowly. Non-renewable resource. Much older water, not very likely to be contaminated by anthropogenic chemicals because there's not a huge recharge area where our toxins can get to it. It's unsustainable on a larger scale, and the rate of recharge a lot of times cannot keep up with the amount of water that we end up sucking out of them. Your unconfined aquifer is great because it's recharged often through precipitation. We have great aquifers in New Jersey for that reason. We have a lot of porous soil. But a lot of the water is contaminated with chemicals and pollution because it's coming from the surface and it's contaminated with anthropogenic stuff. All right. We saw a bit of this already. We have urban areas. We've built up a lot. And before we built in a lot of these areas, a lot of our groundwater was being recharged freely. We didn't have a lot of surface water runoff. There was a lot of evaporation into the atmosphere and transpiration from these trees. But then what happens is we build, look, here's a condo community. And now what happens is you get way less groundwater, you get a lot more surface runoff, and then less evaporation and transpiration from those trees. So you're altering the groundwater recharge, you're altering the amount of precipitation that actually flows into surface water through that runoff, and you're altering the atmosphere and the moisture in the atmosphere. So the Ogallala Aquifer is the largest aquifer in the US. It's found under the Great Plains, and that's how the Corn Belt is irrigated. Most of it is groundwater, and that's how you have high rates of salinization as well, because it's groundwater that's being pumped up that has a lot of dissolved salts in it to begin with. These are Kansas crops irrigated by the Ogallala Aquifer. All of the round ones are just center pivot irrigation. And so they're just irrigating basically in a circle around. These are semi-arid areas. So anything that isn't getting irrigated isn't really growing. And then here are US aquifers. I think it's just pretty. And they do kind of match up with a lot of the, like the one here in California. This is a big underground aquifer that actually runs underneath the Sacramento River up here, and I forget what river it is under there. But this one right here, this blue, that's the Ogallala Aquifer. Right? So when we withdraw groundwater, it's great because we have a source of water in an arid or a semi-arid area, but that also comes with a lot of disadvantages as well. So most of these aquifers are renewable resources unless the water is removed faster than it's replenished. And we are pulling water out of our aquifers and out of groundwater faster than it's being replenished. Groundwater depletion is a huge problem, and it's mostly for irrigation. So in Saudi Arabia, you can see it's a desert. And in 1986, that was the picture on the left. On the right-hand side, this is in 2004. It's not some weird glitchy thing. That is irrigation being pumped up from the ground. Right? Overpumping has a lot of harmful effects. It limits your future food production. So now you don't have that water for in the future. You have land subsidence, kind of like with mines. If mines, smaller mine shafts collapse, the land on top of it collapses. This is just large scale subsidence, because if you have same thing, if you have a bunch of gravel in a cup and you pour water into it, when you start sucking out all of that water, those pore spaces are going to start to become more compact. And then as the water is getting sucked out, your surface starts settling down and reshifting. Okay. So in the San Joaquin Valley in California, you can see this is not this is not a pole that was there. These are marked using GIS and satellites. So in 1925, this was the surface of the land. In 1955, this is where the surface of the land was. And in 1977, this is where it is. It's dropped drastically because of the groundwater being pulled out. So the groundwater pulls out and it's just gradually sinking. You live there, you don't notice that. But what ends up happening is over time is almost like a bowl effect. Right? It can cause sinkholes when an underground cavern then collapses. A lot of times these happen in Florida. There are a lot of sinkholes in Florida. And then you have saltwater intrusion. Right? So if you are sucking out water and it's not filling in fast enough, if you are closer to the coast, what you can get is you can get saltwater starting to come in there. All right. So advantages of withdrawing groundwater. It's useful for drinking and irrigation. It's available year round. It exists almost everywhere. It is renewable if it's not overpumped or contaminated. You don't get evaporative losses. It's not like it's being stored in a lake and it's constantly evaporating. And it's a lot cheaper to extract than most surface waters because you don't have to pay for it. However, you get aquifer depletion from overpumping, that subsidence of land. If you have aquifers that are polluted, then you're sucking up that pollution. You have saltwater intrusion in those coastal areas. A lot of these groundwater areas flow into surface water. And a lot of times, if it's contaminated, you have to keep drilling to find fresh water. If your well is running dry, it means that your level of your groundwater has sunk down. So you have to drill even further now to get to the water. Okay. A lot of times you have a lot of pollution, especially in an unconfined aquifer. And according to the EPA, one or more organic chemicals contaminate about 45% of municipal groundwater supplies. So there are a lot of underground tanks that are leaking. Um, every single gas station that you go to, the tanks in it have been replaced within the past 20 years. And that was a big New Jersey initiative in the late 90s, early 2000s now. Right? So in Bangladesh, what happened was a very water scarce area, and the World Health Organization went and they drilled all of these wells and they tested them and everything was fine. And what happened though was they drilled through arsenic rocks containing natural amounts of arsenic. And what happened was these people were now dying from arsenic poisoning and they didn't know it. So more than 112 million people are drinking water with arsenic levels that are 5 to 100 times the legal standards. And you don't know that because what happens is the arsenic leaches out of the well very slowly. So when you first drill a well, your arsenic levels, you don't have them. But then over time they increase and they increase. And that's how you find, people start getting sick and you're like, oh, let's go test the wells. So this just shows where contamination can come from. And over here you have a leaking tank and your water table travels down. So you can be, this is a pump, a well that somebody's getting their drinking water from and their bathing water from. And now it's contaminated. And a lot of times these contaminants are colorless and odorless. And not many people have wells still in Marlborough. But when you do, you have to kind of test it fairly regularly. There are a lot of solutions for this prevention and for cleanup. Most of them is, ban these toxic chemicals, make sure that they're disposed of properly, and to, clean them up. You don't need to know the specific ways of cleanup. All right. So what you're going to do is answer questions in part 1 of the study guide, and we're going to do part 2 in class.